Okay, we're ready. Emily, are you ready?
Yes.
Yes. So today we have Emily Adlam from Western University, who will be talking about contextuality, fine-tuning, and teleological explanation. Emily, thank you very much for accepting our invitation. That was a bit last moment. We really appreciate it, and don't want to waste any of your time. If you're ready, you can go.
Great. So hi, everyone. Thank you so much for the invitation. It's really nice to be here. So yes, today I'd like to talk about this paper, Contextuality, Fine-Tuning, and Teleological Explanation. And the purpose of this paper was really to try to bring together some of the very broad and rich literature that we now have on contextuality, and to try to draw some conclusions about what this all means and where we should go from here. So there are a few new mathematical results in the paper, but I'm not going to explain those in great detail in this talk. Instead, I'll focus on trying to convey the big picture as I see it. So I'll start by giving some definitions of contextuality. I'll then discuss some ideas that are often raised in the literature in connection to contextuality, and I'm going to argue that some of those are perhaps not actually very useful ways of thinking about contextuality. I'll then present what I consider to be the most appropriate way of thinking about contextuality as a form of fine-tuning, and I'll address the question of how we might perhaps explain that fine-tuning. And then finally, if there's time, I will make some comments on some other interesting mathematical frameworks which have been used to study contextuality. So first off, in its original incarnation, contextuality was associated with the idea that measurement outcomes should be associated with definite pre-existing properties of systems, rather like we expect them to be in the classical world. So in that kind of picture, we can think of a measurement as asking a question like, which of these properties do you currently have? So if measurement outcomes are really like that, then we would expect, given a set of measurements and measurement outcomes, that we could assign the values 1 and 0 to every possible outcome, such that every possible measurement has exactly one outcome with value 1. That's supposed to correspond to the property that the system definitely has, and that's the value that will definitely occur if we perform that measurement. So obviously, if every measurement outcome occurs in exactly one measurement, it's trivial that we can always perform that construction. But of course, in quantum mechanics, for systems of dimension greater than 2, measurement outcomes will typically appear in more than one measurement. So this problem is no longer trivial. And in fact, as shown in the Cauchy-Specker theorem, there exist sets of measurements in quantum mechanics where this construction can no longer be performed. So what that means is that in quantum mechanics, we can't simply interpret measurement outcomes as corresponding to pre-existing properties of systems in the way they do in the classical world. Now, some people have responded to this theorem by saying that quantum mechanics has disproved realism and we can't possibly describe any reality underlying quantum mechanics. So that interpretation is obviously wrong. The Cauchy-Specker theorem doesn't disprove realism as a whole. What it proves is that we have to take a less naive attitude to the relationship between the maths and the reality. We can no longer assume that there's a simple one-to-one relationship between measurement outcomes and properties of reality. But of course, there are many other ways that reality could be that are less like a literal reading of the formalism. So, that doesn't mean we should give up on realism altogether. So the idea of contextuality was subsequently generalized by Rob Speckens to deal with cases where we're no longer making this naive assumption about the relationship between the maths and the reality. So to do that, Speckens used the ontological models framework. That's a framework in which we suppose that all systems at all times have a real underlying ontic state. And then preparations are modeled as probability distributions over ontic states, which are supposed to represent the probability that when I perform a certain preparation, I will get the corresponding ontic state. Then measurements and outcomes are each associated with a response function, which is supposed to tell me the probability that if I perform this measurement when the system is in this ontic state, I will get this measurement outcome. So Speckens then argued that we could have a generalized notion of contextuality where we where we say that we have contextuality if there exists a mismatch between the structure of the ontological model and the structure of the operational statistics. So that gives rise to various different ways in which ontological models can be contextual or non-contextual. So, for example, we say an ontological model is preparation non-contextual if all preparations that prepare the same quantum state are represented by the same probability distribution in the ontological model. Similarly, we say an ontological model is measurement non-contextual if a quantum mechanical measurement operator or outcome is always represented by the same response function, no matter which measurement it's appearing in. So Speckens then showed that, in fact, there can't possibly be any preparation non-contextual ontological model for quantum mechanics. And that's essentially because different probabilistic decompositions of the same mixed state will necessarily have to be represented in different ways in the ontological model. So we therefore have that mismatch between the underlying ontic structure and the operational reality. And similarly, Speckens also showed that under fairly plausible assumptions, there can't be a measurement non-contextual ontological model either. So the question I now want to ask is, why should we care about all this? What does it mean about reality? And what should we do? So there are various things that have been said in the literature about why contextuality is perhaps weird or problematic. Something that's often mentioned is a principle known as Leibniz's principle. My cat is called Leibniz, so the photo is not totally gratuitous. So Leibniz's principle says that if we have two objects and those objects have exactly the same set of properties, those objects must necessarily be, in fact, numerically identical. They're one and the same thing. They can't possibly be different things. So I can sort of see how people think this might be relevant to contextuality. The idea is that we have, say, two preparations and they have the same operational properties, so therefore they must be kind of the same at the ontic level. But unfortunately, I think this is not, in fact, a correct application of Leibniz's principle, because Leibniz's principle is supposed to be a metaphysical thesis about numerical identity. It's about what it is for two things to be literally one and the same thing. Whereas in the contextuality case, we're typically dealing with a situation where we have two different preparations, they involve different operational procedures, they perhaps take place in different places and are performed by different people. So there's no question that those two procedures could be in any sense numerically identical. The question we want to ask is, given that they look qualitatively similar, are there any inferences we can make about what's going on underneath? So at best, those two instances could be two different instances of the same type of thing, but they certainly can't be numerically identical in any sense. So this is really an epistemic question about what inferences we can make, rather than a metaphysical question about the nature of numerical identity. So I think Leibniz's principle is just not relevant here. And I'm not just saying that to be kind of a stickler for historical accuracy. I do think that invoking Leibniz's principle in these discussions is just confusing people and is kind of tending to obscure the issues that are really at stake. It's also just not very useful, because if Leibniz's principle were violated by contextuality, all we could really do about that would be say, so much the worse for Leibniz's principle. There would be no explanation to be offered. Whereas, as we'll shortly see, I think that there are possible explanations for contextual phenomena. Another set of ideas that's commonly invoked in discussions of contextuality are the various things that Einstein has said. And in particular, people like to quote this iconic line with which Einstein opens his 1905 paper on relativity, telling us that we should get rid of, from our theories, asymmetries which do not appear to be inherent in the phenomena. So Einstein here is talking about absolute space. He's noting that the Newtonian theory based on absolute space has a variety of asymmetries and preferred reference frames which don't appear to have any analog at all in the empirical statistics. So he's observing that we can just get rid of those asymmetries very easily without losing any of the empirical content of the theory. So he's basically invoking Occam's razor, saying we don't need this, let's get rid of it. So the contextuality case is really not like that at all, because the whole point of these contextuality theorems is precisely to show that contextuality is inherent in the phenomena. It is built into the operational structure of quantum mechanics, and there's nothing we can do to get rid of it. So if this were really the same as the Einstein case, presumably these contextuality theorems would have been the end of the story and people would have just moved on. But obviously that hasn't happened. There is still a very active discussion around contextuality. So I think there must be something else going on here. Moreover, again, this way of thinking about things just isn't very useful, because we can't follow Einstein's advice here. So there appears to be no viable course of action to sort of move forward from this way of thinking about contextuality. So to see what contextuality is about, I think it's helpful to take a step back and think about what a non-contextual model might look like. And one way to construct a non-contextual model would be to change the conceptual model we have of measurement so that instead of asking a question like, which one of these properties do you currently have? A measurement is understood as asking a question like, which one of these options do you prefer? So in that kind of conceptual model, it's very straightforward to see why it should be that whether or not I get a certain measurement outcome should depend on what the other possible outcomes are. Because, obviously, if I prefer A to B and I prefer B to C, then if my options are A and B, I'm not going to choose B. But if my options are B and C, then I will choose B. So whether or not I choose B does depend on the context. So a model of this kind was explicitly put out by Rudolph some time ago. He suggested we should think of measurement outcomes as vectors on spheres, and the state is supposed to be thought of as like a marble, which is attracted to the nearest or the most preferred outcome. So the measurement contextuality and quotient-Becker contextuality looks extremely natural in this kind of model, so natural that indeed one might start to wonder why anyone ever thought it was a problem. But there is, in fact, a reason why it's a problem, and that reason is Gleason's property, the fact that in quantum mechanics, for a given state, the probability of obtaining a given measurement outcome is always the same, regardless of which measurement we're performing. So if you want to construct a model which combines this preference order type way of thinking about measurements with Gleason's property, and I know this because I've tried, you have to do a lot of very painful and painstaking adjusting of the parameters of your model to make sure that the dependence on context exactly cancels out during the averaging process so that that dependence can't be seen at the level of the operational statistics. Which is to say, of course, what we have is a fine-tuning problem. The real issue with contextuality, in my view, is precisely that we have this mismatch between the ontext reality and the operational reality requires us to do very strange things to the ontic model to make such that the context dependence exactly disappears and can't be seen at the operational level. So that, in my view, is kind of what's really at the heart of the problem with contextuality. So Cavalcanti has used the framework of causal models to show formally that indeed any set of experiments violating a quotient-Becker inequality must be fine-tuned. So the causal modeling framework describes causal influences between the variables involved and possibly some set of latent or hidden variables in terms of a causal model represented as a directed acyclic graph. And we say that a causal model is fine-tuned if its causal graph shows a causal connection between two variables which are conditionally independent at the level of the operational statistics. So it's quite straightforward to see how quotient-Becker contextuality is fine-tuned in this sense, because we necessarily have independence between whether or not I get this measurement outcome and the measurement context. That's Gleason's property. But the context dependence shown in the contextuality theorems demonstrates that at least sometimes we will need to have a causal connection between those two variables. So that is precisely the definition of fine-tuning according to the causal modeling framework. And one might well wonder, other forms of contextuality also fine-tuning issues in the same way. And indeed, that is the case. I use the causal modeling framework in this paper to show that preparation contextuality is a form of fine-tuning in the same sort of way, because in a case where we have two different preparations preparing the same quantum state, we necessarily have conditional independence at the level of the statistics between which preparation I choose and the results of subsequent measurements. But the contextuality theorems demonstrate that at least sometimes there will have to be a causal connection in the causal graph. So again, this is a fine-tuning issue. So I think this fine-tuning approach to contextuality is more useful than other paradigms for several reasons. First off, it allows us to unify contextuality with non-locality and make sense of the connections there, because it was shown by Wood and Speckens some years ago that non-locality is also fine-tuned. That is to say, if you want a causal model which exhibits non-locality but also non-signaling, you have to fine-tune your causal model to do that in just the same way as if you want a causal model which is context-dependent but obeys Gleason's property, you have to fine-tune your model to do that. So that allows us to kind of see these two phenomena as manifestations of the same underlying problem in quantum mechanics. And the other reason this is useful is because if contextuality is a fine-tuning problem, then there's something we can do about it. We can ask, where does this fine-tuning come from? How can we explain it? So I'm going to address that question in a moment, but I want to stop to reinforce that the fine-tuning involved with contextuality and non-locality is not really the same kind of thing as the fine-tuning that appears in various other fine-tuning arguments throughout physics about things like the cosmological constant. So those arguments are typically very theory-dependent. They involve a mismatch between the prediction of some theory and the observations that we've made. So in that kind of case, it's always open to us to say there's no real fine-tuning in reality. There's just some problem with our model. Whereas in the contextuality and non-locality cases, the fine-tuning has been proved using just the operational statistics. It uses just the causal modeling framework. So in that case, it doesn't rely on any assumptions about an underlying theory. So in that sense, this kind of fine-tuning really is present in reality. It's some inherent feature of the operational statistics. And thus, in my view, it seems both a deeper problem and one that is more urgent to find an explanation for. So what can we do if we want to explain fine-tuning? Obviously, we do always have the route of just accepting the existence of fine-tuning. That's what some early versions of superdeterminism do. We can also just deny the problem by becoming anti-realists, saying that there is no model underlying quantum mechanics and therefore there is nothing to be fine-tuned. I find both of these routes not very interesting and they don't seem to lead anywhere useful, so I won't pursue them any further. So if we are realists and we do want to explain contextuality, what options do we have? So I can see sort of two main routes. There's one is the route that is often mentioned in the causal modeling literature itself, and that's the idea of giving an equilibration explanation. So that would involve postulating some dynamical process such that we can start out with more or less any arbitrary distribution, and then over the course of ordinary dynamical evolution, the distribution will tend over time to approach the fine-tuned distribution. So the fine-tuning can then be understood as a natural consequence of normal dynamical evolution. So that kind of route is in fact pursued by some proponents of the de Broglie-Bohm interpretation. They have argued that the de Broglie-Bohm particles can start out in more or less any arbitrary distribution at the start of time, and following normal evolution via the de Broglie-Bohm equations, those particles will come closer and closer to the necessary the distribution that's necessary to reproduce the observed quantum statistics. So that, I think, is a really nice feature of de Broglie-Bohm. And indeed, I think it's not emphasized enough in the literature that the de Broglie-Bohm interpretation does have an answer to this fine-tuning issue, whereas nearly all existing interpretations of quantum mechanics just tend to ignore this problem entirely. That said, there are some awkward things about this account of the fine-tuning. In particular, it implies that we should expect that in the very early universe, these fine-tuned features did not hold. So in the early universe, we should see violations of no signaling and violations of Gleason's property. So obviously violations of no signaling seems to need us to have a preferred reference frame, and that's somewhat awkward if we are committed to relativity. Violations of Gleason's property, we will shortly see, also lead to some nasty consequences. So there are various reasons to think that that kind of feature of the early universe is a bit undesirable. And therefore, for that reason, I myself would prefer to move to an approach which allows us to explain the fine-tuning in a universal way and say that this fine-tuning holds everywhere. So obviously that explanation can't be causal in nature. That's kind of what the causal modeling framework says. So if you are of the inclination that all realist explanations must be causal explanations, you may well think the situation is looking a bit hopeless. However, there are good independent reasons to think that realism shouldn't necessarily be tied to causal explanations. For example, when we look at our fundamental theories, it's very hard to find in them anything that looks like an asymmetric causal relation. So there are good reasons to think that causation is kind of an emergent human phenomenon and not present at the most fundamental level, which suggests that perhaps we should move to a form of realism which, rather than using causation as its fundamental relation, uses some more symmetric and reciprocal modal relation. So that would mean in particular that rather than the causal modeling framework's expectation of a diagram which is acyclic, we would be drawing diagrams of influence which are allowed to have cycles and which are allowed to have symmetric relations between events. Now that obviously helps with the fine-tuning situation, because you can't even get the fine-tuning proof started if you're no longer using a directed acyclic graph. So in that sense, as soon as we move away from this assumption of asymmetric modal relations, we no longer have a fine-tuning problem. Moreover, once we move to this kind of less causal picture, there are a variety of new possibilities for explanation that open up to us. So in particular, if we're no longer assuming that there's some sort of asymmetric network of relationships between the events that we're dealing with, then the natural thing is, then it can't be the case that they come into being in some particular order. And the natural thing to do is to suppose that in some sense they all come into being all at once in some kind of atemporal external way. Which means that we have the option of imposing constraints on the whole distribution and providing what I would refer to as a teleological or goal-directed explanation, where we require that the events we're dealing with must obey certain conditions. So for example, in that kind of picture, we can simply impose Gleason's property as a constraint, requiring that the distribution should obey it, and that thus means that all the parameters must necessarily turn out to be fine-tuned in the right way. Now, you might well think that sounds a bit too easy. Obviously, we don't want to make explanation too cheap because that would then reduce its heuristic value. So if we are going to move to a strategy of using teleological explanations, we should demand that constraints are not just imposed in an ad hoc way like Gleason's property, but instead we should ask if there are deeper, more fundamental reasons why these particular constraints should hold. And in fact, there is a really good reason why Gleason's property needs to hold. And that's because if Gleason's property failed, it would be possible to use quantum correlations to send signals back in time. So to see that, imagine we have two maximal contextual measurements, one with outcomes A, B, and C, and the other with outcomes A, D, and E. And suppose that Gleason's property doesn't hold for those measurements. So the probability of obtaining the result A in the first measurement is different from the probability of obtaining the result A in the second measurement. Now, we can always split these measurements up into two parts, and we can first perform the measurement A or not A, and then subsequently decide if we're going to perform B, C, or D, E. So obviously, if Gleason's property doesn't hold here, the result of our first measurement, A or not A, will depend on our subsequent decision about whether we want to measure B, C, or D, E. So we will have sent a signal backwards in time. Now, I think it's sort of intuitively clear that sending signals back in time is going to be problematic and is going to lead to various paradoxical things, but let's try to be a bit more precise. So one way to understand the problem with signaling backwards in time is to invoke bilking, which is a concept from the philosophical literature on time travel. So the idea of bilking is that we can get paradoxes in time travel situations where, for example, a time traveler goes back in time, kills his grandfather before his grandfather can father any children. So the time traveler is not born in the first place, and thus logical paradox ensues. Now, one can easily create a similar bilking scenario using signaling backwards in time. So, for example, suppose that I send to my future self a message containing the value of 1 bit. My future self opens the message, flips the value of the bit, and then sends that bit backwards in time back to me, and I then receive that just in time to open it and use it as the content of my original message. So that message now has bit value 0 and bit value 1 at the same time. So we've derived a contradiction. Now, in the contextuality case, it's not quite as easy as that to derive a contradiction, because in the contextuality case, we're not dealing with deterministic signals backwards in time. The signals are only probabilistic. So we're never going to get an outright contradiction where some quantity has 2 different values at the same time. What we will get is that if we perform many compositions like this with processes made into loops, and we repeat those processes many times, and we look at the relative frequencies that we observe in the course of those compositions, we'll find that the relative frequencies that those processes exhibit will have to be different from the relative frequencies that they show when we perform them under ordinary circumstances. So that's certainly a bit weird. There's a sense in which these processes need to know something about the global structure of the way in which they've been composed before they can decide what their outcome is going to be. So there seems to be some sort of failure of locality arising here if processes need to know something about global structure of compositions. So depending on your feelings about the objectivity of probability, locality, and the way things should work under compositions, you may or may not feel that that represents a contradiction. Another way of seeing the problem with signaling backwards in time is to observe that it leads to loops which are necessarily incompatible with determinism. So going back to this example of the bit that's being sent round and round in the loop, the value of that bit is necessarily coming out of nowhere. It can't possibly have an external cause anywhere in the universe outside the loop. So that loop is therefore indeterministic in a really strong sense. There's absolutely no possibility of it being determined by anything, no matter how non-local you allow that determination to be. So that kind of loop is incompatible with a notion of global determinism. So if we insist that the universe must be deterministic in some sense on a large scale, it necessarily follows that we can't have closed loops like that, and therefore we can't have processes that would send signals back in time, and therefore Gleason's property must always hold. And indeed, in an earlier paper, I also showed that similar sorts of reasoning can be used in the signaling case. If you have signaling, then you can similarly create closed loops which are incompatible with determinism. So your mileage may vary, but for me, I think this is a really interesting way of trying to understand what kind of global constraints would lead to this local behavior and this local fine-tuning that we see in quantum mechanics. Okay, so quickly, I just wanted to mention some other really interesting mathematical frameworks that have been used to study contextuality. So one of those is the quantum logic program, which was initiated by Abramsky and Hardy. And what this program does is derive from classical logic an upper bound on the sum of probabilities for various sets of measurement outcomes. So we treat measurement outcomes as Boolean variables, apply the laws of classical logic, and thus derive inequalities which it turns out are violated. So that seems pretty weird. And so there are two different ways that we might interpret that result. One is to say that, well, evidently classical logic just doesn't work in the quantum world. There must be some kind of special quantum logic that governs quantum reality. The other possibility is to say that, no, classical logic still works perfectly fine in the quantum world, but quantum measurement outcomes are not the kind of thing which is appropriate to describe as Boolean variables. So a slightly trite example, suppose I offer to you every morning a choice of different breakfast items and you can choose exactly one, and I record which item you choose over a series of days. Then I use those relative frequencies to calculate the value of a logical inequality, and I am surprised to find that your choices violate a logical inequality. I don't think anyone would be inclined to suggest this means that there must be some kind of special non-classical breakfast logic. What's going on here is that it's not appropriate to represent the result of your choice as a Boolean variable because your choice on a given day will, of course, depend on what your other options are. Whether or not you choose bacon might depend on whether or not I also offered you some sausages. So quantum measurement outcomes, I suggest, could be the same kind of thing. And indeed, that's kind of what Rudolph's marble world model was getting at. If we represent quantum measurement outcomes as preference orders rather than as Boolean variables, it's no longer quite so surprising that they violate logical inequalities. And personally, I think the second way of thinking is more useful just because the fact that quantum logic doesn't seem to work right in the quantum world is really exactly what it needs to be explained here. So just postulating the failure of classical logic doesn't to me seem very explanatory. So I don't find that a very useful way of thinking about these results. There have also been very, very many pieces of work showing that there's some relationship between contextuality and some kind of non-classical probabilities. So it's been shown that one can make a contextual model non-contextual if one allows negative probabilities or complex probabilities, or if one relaxes various kinds of standard requirements on probability spaces in the ways I've listed here. So again, I think there are two different ways of interpreting these results. Either we say that quantum reality really does incorporate literally something that looks like a negative probability or a complex probability or what have you, or we say no, quantum reality is still described by standard classical probability, but there's something about quantum reality that makes these negative probabilities or complex probabilities useful in certain sorts of cases. So the problem with the first of these options, in my opinion, is that it's hard to see in which sense these things could possibly be literally probabilities. So negative probabilities can't be subjective probabilities because, as Feinstein and Fletcher have shown in this very nice paper, any agent who sets their probabilities equal to these non-classical probabilities will necessarily violate paradigmatic rationality constraints. So in particular, they will accept a bet which is guaranteed to lose. So no rational agent can accept these as their subjective probabilities. Can they be objective probabilities? Again, I don't think so, because the one thing we really know about objective probabilities is that, as the principal principle, the idea that a rational agent who knows the objective probabilities would set their subjective probabilities equal to them. And we've just seen that rational agents can't set their subjective probabilities equal to these non-classical probabilities. So again, it doesn't seem that they can be objective probabilities either. So I personally can't really see any sense in which these things could literally be probabilities. On the other hand, I can see ways in which they could emerge naturally out of certain mathematical constructions. So in the paper, I give an example of this, and I show that if you take a normal, totally classical ontological model, which is contextual, you can always compress that model to a model which is non-contextual, and which is defined on a smaller set of context states at the cost of introducing some negative probabilities. So this, I think, shows quite clearly how this relationship between contextuality and negative probability comes about. It's the result of trying to turn a contextual model into a non-contextual model. But those probabilities are not literally probabilities. They are just artifacts of this mathematical construction in which we move from a contextual model describing real context states to a non-contextual model describing context states which are not supposed to be elements of reality, but which are just artifacts of the construction. So in my view, that kind of construction makes it much less mysterious to see where these negative probabilities come from. There are several other very interesting approaches to contextuality, which I discuss in the paper, including the graph theory approach and the sheaf theory approach, but we're now getting short on time, so I think, again, we should move to questions.
Thank you very much, Emily. And thank you also for respecting exactly the half hour. That's extremely rare. All right, so there was a question in the chat by Lee that I did not see in time that we could start from. And also I'm giving the moderation to Andrea Di Biagio.
Okay.
Hello, everyone.
Let me postpone the question about time and ask a very simple question. At some point, you invoked Lorentz invariance as a reason not to have distance signaling in the very, very early universe. But indeed, Lorentz invariance is a property of a theory. Every state and every solution, except the ground state, to any classical field theory or any quantum field theory violates the symmetries of the theory, including that one. So I don't understand why you invoke a violation of Lorentz invariance to rule out an assumption about the early universe. After all, the cosmological models we find so useful all violate Lorentz invariance and have preferred frames.
Yes, indeed. And so I don't necessarily consider that a totally conclusive argument. I don't think the equilibration approach is ruled out by it. I do think that it is one consideration which might make us uncomfortable and might perhaps make us want to consider other options. In particular, both signaling and violations of Gleason's property can be used to create the kind of loops that I've just sort of finished discussing. And I personally think those loops are at the very least awkward and potentially paradoxical. So that gives us a good reason to try and avoid theories which allow the formation of that kind of loop.
Good, okay, but that's a different reason. And the first comment, I don't know if this is easy to communicate, but there's a view that sometimes appears in the literature, starting with Heisenberg and Dyson and other people, that the quantum description, the quantum state, is a description of, quote, the future, and classical dynamics is a description of the past. In particular, that view holds that the outcome of measurement is always about the past, because the confused measurement is always something that happened in the past. And that, the question is, does that remove some of the sting from non-contextuality?
So if one is sort of explicitly allowing for influences from the future or retrocausality of some kind, that in and of itself doesn't take away the issue with contextuality. So there's a nice paper by Fabio and Costa showing that we still get contextuality even if we do allow some influences from the future. But those kinds of models do still assume that ultimately the causal structure is asymmetrical, because that's what you need to give these fine-tuning arguments. So one way to get rid of that problem is to not only allow influences from the future, but allow those influences to be kind of more symmetric and reciprocal, and that thus we don't get the same mismatch between the attempt to make a causal model and the operational statistics. So taking the future into account in that sense works as long as you're not still making assumptions about asymmetric underlying causal relations.
Okay, thank you.
Carlo, you want to go next?
Thank you, Bill. Thank you, Emily. It's very interesting for me and very troubling at the same time. This QISS meeting they're good because there's this time for discussing things. So it's not just a straightforward question. It's an opening of a point I want to make. Let me put it this way: everything you said, given the starting point you took, it's made completely sense to me. I have no objection whatsoever. I mean, it seems to be to follow very nicely, including your sort of awkward conclusions or challenging conclusions or courageous conclusions, whatever you want to put it. But it's a formulation of the problem which troubles me, and the formulation of the problem is the following: you dismiss anti-realism, and I'm happy with that. So let's not go epistemic in some way. But then you give a very specific, concrete version of what to be realist mean. And I do understand that this is a common definition of realism in a certain domain of research, to the group of people that work in that. And the idea of realism here is that there are ontic states. You use this language often, the sort of underlying quantum mechanics. Quantum mechanics, as we know it, is quantum mechanics, predicts these things. But behind the scenes, there are ontic states, which is what really is going on down there. And that's what realism is about. Now, it seems to me that we're using realism in two completely different meanings here. One is a sort of general philosophical idea of what is to be realist. And another is to say, well, to be realist is to believe this story about quantum mechanics. I can be a realist without believing this story about quantum mechanics. That's the main point I want to make. Namely, it seems to me that the single point I disagree with you is the moment in which you say, well, this is certainly troubling, I agree. What are the options? One option is equilibration, which its own difficulties. One option is the one you seem to like, right? It's a sort of this global in time version, including, okay. And the other options is just to go non-realist. Wait a minute. The other option is not to be non-realist. The other option is to be realist in a different sense. To be realist without thinking that there is mysterious ontic states down there that do the job of quantum mechanics. And the reason I'm saying that is because I think that contextuality, as a name, your old stories about contextuality, is older than Koch and Spencer. It's older than Gleason and all that. It goes back to Bohr, and it's a specific idea that I think is the core of quantum mechanics, that the properties of a system depend on the context in which they're measured. So in a sense, there is a non-technical version of contextuality, which is the very denial of the idea that there are ontic states. namely, of course, I mean, you know what I think about quantum mechanics. I come from the relational perspective. In the relational perspective, I want to say it's perfectly realist, and it's stronger than that. Let me put it this way: there is one way. If I would disagree with you with the premises of your discourse, I would say you're being too epistemic about the interpretation of what is a measurement outcome is. If a measurement outcome is it's a description of our epistemic access to an underlying ontology, okay, then we get in trouble. And when we get all this confusion. But if what quantum mechanics call the measurement outcome are the ontology, that's it. There's not underlying mysterious ontology. And this ontology, facts, events, happen contextually, and they don't reveal properties of a system, but are the ontology we're talking about, then we just don't get into this problem. And that's a relational quantum mechanics way out of this. So there's a way of getting out of this, which is to be realist about the measurement outcome and not to interpret them as our sort of epistemic access to an underlying reality, which cuts the problem at the basis, seems to me. Now, you may say, well, but this has other problems and this is not sufficiently realist in some way, but there is this other option, seems to me.
So what I think I'd say to that is that the ontological models framework doesn't necessarily assume that the ontic states are in any sense ontic or hidden. The states in the ontological models framework could just be quantum states, or they could be states of observers, or they could be descriptions of the world. In that it's quite a general idea, which is you don't necessarily need to think of them as being hidden variables in the traditional sense. So I think that saying that the ontic models framework doesn't apply outside sort of hidden variable models isn't correct. And moreover, the kind of the purpose of this framework is to give a mathematical structure in which allows us to kind of formalize the fact that we have some kind of mismatch between the influences that are required to give these correlations and the operational statistics. And whatever you want to say about the nature of those influences, whether you want to say they're causal, whether you want to say that they are some kind of relational thing, the mathematical fact of this mismatch still remains. And it's very possible that there's an explanation of this mismatch that can be given in the relational framework, but I haven't so far seen anyone explicitly deal with it and explain how this special fine-tuned effect arises in the relational framework. And you know, I'd be very interested to see that, but I haven't seen this particular issue addressed yet. In the
but what are the ontic states in the relational framework?
Well, the ontic states whatever the relational framework takes to be real. You know, if
just the measurement outcome, nothing else.
Yes, but the ontic states refer in that case to perhaps the agents who are performing the measurements.
They refer to the no agent. They refer to both systems and the system, the physical part of the world the system is interacting with. The
ontic states could perhaps represent the relation between those two systems, or whatever this picture takes to be real. You know, if it's a realist picture, there must be something which is real, and that's what the ontic states are.
Lee wants to say something here.
Yes, there's more than one relational ontology. For example, there's a relational ontology in which what is real is the view of every event, of some events near it or interaction with it, which I think is very just hard-nosed realist. It says what exists is these views.
And that could, the view of everything that exists could be an ontic state. So the ontological models framework isn't necessarily to be taken very literally, but it is a useful way of kind of expressing why it is we feel there's something weird about contextuality, that there at least perceived to be some mismatch between the operational statistics and what is going on underneath. And And I think any interpretation has a duty to explain.
But why should be something going on underneath?
Well, there doesn't have to be something going on underneath, but there's a mismatch between the operational statistics and kind of our pre-philosophical intuitions about what kinds of things could be going on underneath.
I agree, but that's our whatever the special use philosophical intuition, what goes on underneath. If nothing, so if systems have no properties,
yes,
by themselves, which is the hypothesis of relational mechanics, and if what we mean by properties is what happen at interactions, then the framework collapses on line one.
Well, I agree that the fine-tuning argument can't be made in that scenario, but I think there still remains a duty to give an explanation of the specific nature of these correlations, the fact that we get correlations which look to us to have a mismatch. There's a need to explain why this particular type of correlations arise within the relational framework. Similarly, in the account that I gave, moving away from asymmetric relations immediately makes it impossible to make the fine-tuning argument, so there's no problem. But then I also want to understand what is it in this framework that gives rise to these correlations of this specific form, and that's what the rest of the argument is intended to do. And that's what I'd like to see in the relational framework, not just well, there's no problem, but also this is why we get correlations that have this form.
I'll shut up then. But if I study quantum mechanics, okay, and I study the transition amplitude of quantum mechanics, there's nothing mysterious apart the fact that if I ask questions like what is the actual state of the things, what is the properties, the kind of question that Koch and Spencer were asking, right?
But
what are the probability distribution of some variables when I'm not looking at them? Okay, that's the kind of question that if these questions as a part of the old discussion of quantum mechanics claimed are not questions about reality, because there's nothing real there. So if properties have no value, so the quantum logic part.
It is very easy to see why, in a relational perspective, why we should have context dependence. Of course, that's easy. What is less easy is to see why we should have Gleason's property. So Gleason's property is what kind of motivates the belief that measurement outcomes represent pre-existing properties in the first place. It makes them look like pre-existing properties. And so there's a mismatch between the existence of context dependence and the appearance that they kind of act like pre-existing properties in some scenarios. And so what's needed is some account which explains why we get this mismatch between Gleason's property and also having context dependence.
I don't want to monopolize that discussion too much. Maybe we should discuss Gleason property separately. I think Gleason property is just, the transition amplitudes, it's exactly capturing the part where the context is not relevant in the standard for relational quantum mechanics, right? It tells you, given a preparation, the probability of seeing that state is that, independently of what else you're measuring around. So
so the thing is that
capture where there is a relation, and it is assumption that there is some underlying reality that has properties nevertheless that around the obvious. Gleason property is obvious by itself if you don't think in terms of contextuality, right? It's just the obvious thing you would expect. It's true in classical mechanics. Is that if you realize as a contextuality and you assume that that there is an underlying reality, then Gleason property seems strange because but this is the assumption that there's an extra underlying reality of which we have to talk about.
Gleason's property
that creates the problem.
What makes Gleason's property seem strange is the context dependence, regardless of whether or not there's an underlying reality. So the question for the relational interpretation is, presumably it could have been the case that we had context dependence, and that would typically not lead to Gleason's property holding. So the question is, if context dependence is so natural and normal in this framework, why then does Gleason's property hold? Why do measurement outcomes act a bit like they are pre-existing properties, even though they're not?
Because it's also only one aspect of context that matters, not the full of it. The specific question I'm asking, and not the others.
Right, but why does the specific question you're asking not affect the probability? One would think that it could have changed the probability if we have generic context dependence. So that the question is, why does that context dependence exactly disappear when we look at the probabilities?
All right, fine. But is that a bit sufficiently strong for me to take seriously that there is causation for the future?
Well, that is one possible explanation. I personally find causation for the future plausible for independent reasons, so that's why I'm drawn to it. But I'm not saying it's the only possible explanation. But I do, I would like more people to consider this issue and come up with their own explanations.
Okay. Yep. Okay. Good. That was a good discussion. Thank you.
All right. There was Lorenzo Catani.
Yeah, hi, Emily. Actually, let me comment very briefly on this last matter before asking the question. So I think what a relational approach should do to solve the fine-tuning problem is to provide a theory-independent mathematical framework where it's clear what is the reality described, like the ontological model framework, and then show that you cannot run a no-go theorem like Cohen-Specker theorem. So actually, that would become a go theorem. Okay, so you define what are the ontic states, the relations, if you want, in this framework, then run the same argument that you run to explain Gleason's property, but show that this time you don't have a no-go theorem, so you don't involve into fine-tunings. That would be the solution.
Great, I'd love that. Yeah,
it's required from relational quantum mechanics. Anyway, this was
thanks.
Apart. What I wanted to ask, which is somehow like related to this, is so usually the kind of solutions I see to the fine-tuning problems, I divide them into two ways. One, which is explain the fine-tuning as emergent, like for example, the equilibration example you showed, or changing the ontological model framework into a framework, for example, a relational framework or whatever framework you want, such that you don't run into fine-tuning problems. So your approach with all at once approach, I'm not sure to which of the two categories to put it, because from one point of view, I think that is like the equilibration process. So you say that oh look, actually there is a physical mechanism or property that I didn't know, which is forbidding these closed and deterministic causal loops, such that now it's natural that I have the fine-tuning. Or instead, you prefer to think about it as saying that no, actually this all-at-once approach requires a new ontological framework different from the standard ontological model framework, such that there is no fine-tuning. Which of the two, or?
I can see it in both categories. I think I tend to think about it in probably requiring a new ontological framework, in that a lot of the ways we think about causal models and ontological models is in a very causal way. We expect asymmetric causal relations. And as I've said, I don't think there's any good reason to believe that there are asymmetric causal relations at a fundamental level. So we should be building a way of thinking about ontology that doesn't presuppose asymmetric causal relations. And that would look quite different, and that would not have a fine-tuning problem.
Okay.
There was a message from Nick Ormerod from the quantum group. I don't know if you're there and you want to unmute, or I can just read it. Okay, well, it seems not to be there. So I think, oh, no, there you go.
Hi. Yeah, so my question was just, if I understood correctly, a lot of the issue that you were trying to address was this this fine-tuning problem that's associated with contextuality. And if I understand correctly, that fine-tuning is a feature of an explanation of the measurement process provided by a classical causal model, right? So fine-tuning is a feature of a classical causal explanation. It seems like another viable option for the realist to overcome this kind of problem with fine-tuning is just to reject the classical framework for causal explanation, which seems like a pretty plausible thing to do, given that it assumes that the basic relative causal relations are classical variables, whereas in quantum theory we're not expecting that classical variables form a fundamental part of our ontology. So I wonder whether you thought about that alternative kind of solution to this problem, or whether you've got any particular reasons for not liking that approach.
Well, I think that is more or less the approach I took. My conclusion was that we shouldn't assume causal relations are fundamental, and thus we should reject the classical causal model framework. So I think I'm not quite sure how that's different from what I proposed. I would note that at least some of the variables that are involved in these causal models are classical variables, in the sense that they're the results of measurements, and we can see them and write them down and so on. So they're basically as classical as anything ever is. The latent variables could potentially be non-classical in some way, but if one is going to reject the causal modeling framework on the basis that the latent variables are not classical, I would like to know what exactly is non-classical about them and how that prevents the fine-tuning problem from taking hold.
Okay, fair enough.
I have a question for you, Emily. Thanks for the talk. So I wanted to go back to one point where you were inside your teleological sort of explanation, and I think if I understood correctly, you were motivating the presence of Gleason non-contextuality, so as to avoid signaling towards the past, right? Yes. In the case of agents. And I wanted to ask you more, if you could elaborate more on like your argument was based on the fact that an agent could decide based on the measurement that they could, if I contextuality, you can, like an agent could decide, depending on what they received in the present, they could decide to change their actions in the future, and so send a message in the past or something like that. But isn't there a tension between assuming that an agent could make that choice, given that you're already looking at some kind of loopy causal explanations? What do you think about
that? So you're proposing, rather than preventing signaling backwards in time, we should take away the free will of agents to compose processes in various ways. Yes, that would be another way to prevent loops forming. And I have no particular argument against that. But the observation I'm making is that it kind of seems as if the universe works very hard to make it impossible for loops to form. It doesn't let us signal back in time. It doesn't let us do superluminal signaling. Everything seems very carefully adjusted to stop loops from forming. So it kind of looks to me as if the route the universe has taken is, rather than restrict the free will of agents to compose things, just don't allow any processes which could lead to paradoxes. So as far as I can see, that is the way things actually work, although, the universe could also have chosen to restrict free will instead. That would have been another way to avoid paradox.
Right. So I see, because in the end, the free will of an agent can also just be seen as a variable that's uncorrelated, that's making that choice, right?
Obviously, agents are physical systems. they are subject to constraints. But as far as I can tell, that we don't tend to be subject to limits on the way in which we can compose processes. I've never seen that. So it sort of seems as if, in reality, our ability to compose things is not restricted, and what is restricted is the existence of certain types of processes.
Can I follow up on Andrea, if there's nobody else?
There's nobody in line at the moment.
Okay, so let me follow up on that. Let me try to reformulate something that it's related to what Andrea was saying. Let me put it this way. I mean, this comes from the perspective that that I have, Andrea has, and I think, Emily, you share, about direction of time. So the freedom of the agency being involved here is not so much the freedom of the agency, it's the possibility of agency of affecting the future and not the past. So it's a oriented freedom of the agency. And this is used by Cavalcante in his derivation of the fine-tuning. So I guess I would ask the following question. Suppose I think that this is only thermodynamics gradient, and would it be possible to redo the Cavalcanti argument for fine-tuning in a non-time oriented way without bringing in this sort of non-fundamental, perhaps, time orientation, and just use some time symmetric analog of the no signaling to the future, which exists, to get the same result?
Yes, so there is a paper which does that by Shrapnel and Costa, where they demonstrate the existence of contextuality even if you allow for retrocausality. So what is the fine-tuning issue comes not from the direction of time per se, but from the assumption that we can represent things as a directed acyclic graph. So if you allow retrocausality, but you still insist that somehow there are no cycles in your graph, then you'll still have fine-tuning. Whereas if you allow retrocausality, but you no longer insist on the absence of cycles, then the fine-tuning problem does go away.
Okay, thanks. Lee?
Yes, I want to speak up for the view that the direction of time is fundamentally asymmetric, and there is a huge difference between the past and the future, and it matters exactly for these kinds of questions. And I mentioned that was what the first comment was about. But I think that when we're talking about different kinds of realism and relationalism, I think the kind of relationalism and realism that I find the way out of all these conundrums is the idea that the universe has many partial sets of things that are real and true. They all involve the causal past of events. What an event is in some sense a partial sampling of information about its nearby causal past. None of these views are complete. No observer has a complete description of all the beables. And I think that allows us to have the kind of quantum mechanics we use and love in small subsystems of the universe, and prevents us from running into many, I won't say all because I haven't looked at all, but many of these so-called paradoxes and confusions.
Yes, that does seem, again, the kind of route which could lead to a very satisfying answer to this fine-tuning problem. Again, I would sort of want a specific account of how this mismatch between context dependence and Gleason's property emerges based on that view. But I'm sure there is an account that can be given in that picture.
Good. Well, let's do it.
All right. Are there any other people that want to speak or ask questions to Emily? Well, it seems that nobody else has a question. So let's thank Emily again for giving us this talk and answering all these questions.
Thank you.
And
Thank
see you all soon for the next QISS virtual seminar.
Who is the next speaker?
I actually don't know, but I can check quickly.
Richard Hall with the Van Eyck on non-Gaussianity. So an experimental test for showing that gravity is non-classical using so by detecting non-Gaussianity production in Bose-Einstein condensates.
Great. Thank you very much.
Thank you, Emily.
Thank you, everybody.